Dear student, warm welcome to NPTEL Phase 2 program video course on geosynthetics engineering in theory and practice. My name is Professor J. N. Mandal, Department of Civil Engineering, Indian Institute of Technology, Bombay, Mumbai, India. This is lecture number 38. This module 7, lecture number 38, geosynthetics for steep slope. Now I focus the recap of the previous lecture. The design example on limit equilibrium design approach and Scammerdmann's simple sliding wedge method. You have observed in case of Scammerdmann ETL design approach, and we use the gradually decrease the length of the reinforcement. There is a reinforcement at the top and also there is a reinforcement at the bottom of the reinforced soil slope, and the length of the geogit material is variable. In case of Scammerdmann ETL design chart which we have covered. In addition, the potential failure surface is curved, that is the logarithmic spiral, and this design chart is good and this also more accurate. But now we will address the design method by Juels, and he has developed the two parts wedge mechanism, and this method however is suitable for the low and the medium walls, and it is more conservative approach, and this dual method is relatively better, and we will address this Juels method in this course. Now, in this dual method, we have considered the limit equilibrium method can be used. So, for an example, what will be the definition for the analysis of steep reinforced soil slope? So, if we draw a slope, and this is the slope, steep slope, and which is making at an angle beta, and you can place a number of the layer of the reinforcement. So, this is number of layer of reinforcement, and in dual method we have considered the two wedge method. So, it has a two wedge. Suppose this is the wedge 1 and this is the wedge 2. So, this is the limit equilibrium method, can be used in the form of two parts wedge surface as it is shown, and if the height of the slope is equal to, this is h, and there is also the surcharge load, and which is designated as W of S, and this slope also has a properties of the soil. We know that what will be the gamma, what should be the unit weight of the soil, and also what will be the angle of friction, that is pi. And apart from that, there is a pore water pressure which can be designated of R of U. So, R of U is equal to U by gamma Z. For example, that if you want to determine that what would be the pore water pressure at the depth of, let us say, Z of 1 at this point. So, you can calculate it R of U. So, R of U here will be U divided by gamma of Z1. Let us say that it is a U1. So, you can write RU is equal to U1 by gamma of Z1. For example, if you want to determine that what will be the pore water pressure in here. So, let us say this is located at a depth of Z of 2. So, RU will be equal to U2 by gamma of Z2. So, like this you can calculate what will be the pore water pressure, and this is the length of the geogrid. Let us say this is L of R. So, this is the definition for the analysis of steep rainfall soil slope, which is Jewell, is given by 1991. And you can use also the primary geogrid, uniaxial geogrid material, or also you can use the secondary uniaxial geogrid material. Now, here develop the number of the design chart for varying the pore water pressure and also the slope angle and the varying properties of the soil. So, now you can see here Jewell method for slope stability, and this is the two parts wedge. This is wedge 1 and this is wedge 2, and the slope angle is beta, and this here for wedge 1 this is angle of theta 1, and this for wedge 2 it is making angle of theta 2, and this coordinate is x and y. So, this is from here to here is x, and from here to here is y. And for the wedge 1, this has a tensile strength of the geogrid material T1, and for the wedge 2, tensile strength of the geogrid material T2, and this is height of the slope, and this is the surcharge Q, and this is the properties of the soil. That means you know what is angle of friction of the soil, what will be the cohesion value, what will be the unit weight of the soil, and also what is RU, what is pore water pressure RU. Here this is the two parts wedge mechanism. Though in case of the cantonment we adopted that only as a potential failure surface is a curve or the logarithms spiral, but in this case in the Jewell's analysis we have considered the two wedge mathematics. So, two wedge system, and this will be much more applicable for the low and the medium types of the reinforced soil wall. It is also say that more conservative, and Jewell chart will be much more suitable. So, here the tensile strength is T1 and T2. So, total tensile strength of the geosynthetics will be T1 and the T of 2. So, this is the equation. Ultimately, you will get T total is equal to T1 plus T2 is equal to W1 plus Q1 into tan theta 1 minus tan pi 1 dash plus U L into tan of pi dash minus K1 divided by cos theta I plus this W2 plus Q2 tan theta 2 minus lambda 2 tan theta 2 dash into lambda S into E2 into tan of theta 2 dash minus K2 divided by cos theta 2 divided by 1 plus lambda S tan theta 2 into tan theta 2 dash. And this is the Z of I at any depth. This is H is equal to root of I minus 1 by L minus Q by gamma. What W1 is equal to weight of the wedge for 1, that is kilonewton per meter. W2 is weight of the wedge 2, that is kilonewton per meter, and Q1 is the surcharge on the wedge 1, Q2 is surcharge on wedge 2, X is equal to the X coordinate of the two parts wedge mode, that is in meter, Y the Y coordinate of the two parts wedge node, that is in meter, beta is the slope phase angle in degree, gamma unit weight of the soil kilonewton per meter cube, theta 1 base angle of wedge 1 in degree. So, this is what is wedge 1 and wedge degree, this is theta 1, theta 2, this. Yeah. Next, theta 2 is equal to base angle of wedge 2 in degree, lambda S is base sliding factor, pi 1 dash angle of internal friction at base of wedge 1 measured under effective stress condition in degree, pi 2 dash angle of internal friction at base of wedge 2 measured under effective stress condition in degree. T1 sum of the reinforcement forces acting on wedge 1 kilonewton per meter, T2 sum of the reinforcement forces acting on wedge 2 kilonewton per meter. Based on this theory, Joule has developed some also chart, and then U is equal to pore water pressure kilonewton per meter square, U1 is the pore water pressure acting on the base of the wedge 1 kilonewton per meter square, U2 is equal to pore water pressure acting on base of the wedge 2 kilonewton per meter square, K1 cohesive force acting on base of the wedge 1 kilonewton per meter, and K2 cohesive force acting on base of the wedge 2 kilonewton per meter, and Zi is the depth to ith grid, and H is overall height of reinforced soil slope. N is equal to number of geogrid layer, and Q is equal to surcharge. So, based on this equation, Joule developed the design chart for the steep soil slope in the form of a 2 parts wedge surface. I say this is limited equilibrium method have been used, and length and the spacing of geogrid reinforcement under different pore water pressure can be determined. So, this here that Joule has developed the steep reinforced soil design chart for varying the various pore water pressure ratio. So, that is Ru is equal to U by gamma Z, and this Ru value may be 0, or Ru value may be 0.25, or Ru value may be 0.50. So, in each case of the pore water pressure, let us say when Ru is equal to 0, and he has developed a design chart which is related between the K required and the slope angle for the particular the pi value. That means what will be the minimum required forces, that is K required. So, K required you can determine one of the chart knowing the slope angle and the pi value, then you can determine what will be the minimum required force, that is K required. And also under the same pore water pressure RU is equal to 0, you can also determine for the another chart, which is the correlation between the beta and the what we call the minimum required length overall stability, that is LR by H overturning. So, knowing the value of the beta, you can calculate what will be the LR by H, and similarly you are to determine what will be the minimum required length of sliding, that means LR by H due to direct sliding. So, if you know that what will be the angle beta and the pi, then you can calculate that what is LR by H due to sliding. So, I am just representing here, this is the design chart for the steep reinforced slope with the pore water ratio is RU is equal to 0. This is given by Jewell 1991. This is the steep reinforced slope design chart, and this chart is the minimum required forces Kr which you have to determine. So, knowing the value of beta and the pi, then you can determine K required. Similarly, from this chart you can determine what will be the minimum required length overturning stability. So, knowing beta and then a pi, and then you can determine what is minimum required length for overturning stability. And this also the minimum required length for direct sliding, you know the beta and the pi, and then you can calculate the what will be the LR by H due to sliding. Like that, he has developed the different chart for the various pore water pressure. So, this is the same nature of the curve, but the pore water pressure RU is 0.25. So, next also this is a design chart for steep reinforced slope with pore water pressure RU is 0.50. So, first of all you can check that what will be the RU, and then accordingly you can design for slope stability using the Jewell design chart. So, from the Jewell design chart, if you know the pore water pressure ratio, you know the what will be the properties of the soil and the height and the slope, then you can determine what will be the length of the reinforcement, and also you can determine what will be the spacing between the reinforcement. The outline of design procedure is mentioned below. Step 1, you have to select the required geometry of the slope structure, that is what is the height H and the slope angle beta and surcharge loading Ws. Step 2, select the soil unit weight, angle of friction of the soil pi dash and coefficient of pore water pressure Ru. Here Ru is the ratio of pore water pressure at depth Z due to the vertical pressure at depth Z, that is Ru is equal to U by gamma Z. That value may be the 0, 0.25 and 0.50. Step 3, determine the earth pressure coefficient K required from the Jewell chart based on the pore water pressure ratio, that means Ru. Step 4, determine the ratio of length of the reinforcement to the height of the embankment, that means L by H from the Jewell chart based on the coefficient of pore water pressure, that is Ru. So, whether Ru value is 0, then you can select what will be the length to the height ratio, or if the Ru value is 0.25 or Ru value is 0.50, then accordingly from the design chart you can calculate what will be the length to height ratio of the embankment. So, minimum length at the crest of the slope is that required for the overall stability, and minimum length at the base of the slope is greater of the two required for overall stability L overall and for preventing the direct sliding LDS. When the reinforcement of constant length are to be used, select the greater length between the L overturning and the L direct sliding. When the direct sliding govern, it is permissible to reduce the length uniformly from length due to direct sliding LDS at the base of the slope to L overturning L OBRL at the crest of the slope. So, this is the some point has been given by the Jewell, and this will be the much more clear when I will give one example related on the steep reinforced soil slope, and we will see that how we can make use of the design chart given by the Jewell and how that length it can be selected based on the direct sliding and overall stability. Step 5, determine the effective slope height H dash as follow. So, H dash is equal to H plus WS by gamma W. You know WS is equal to surcharge loading. So, you can calculate that what will be the height of the slope due to the surcharge. Step 6, determine the safe design strength of geogrid reinforcement, that means T design. So, T design will be equal to T ultimate divided by overall factor of safety into reduction factor. Step 7, select the minimum vertical spacing, that V. The spacing constant Q can be written as Q is equal to safe design strength of geogrid, that is T design divided by K into gamma into V. So, you should remember what is Q, that is spacing constant, that means Q is equal to T design by K into gamma into V. So, we will use this equation when we will design the reinforced steep slope using the Jewell chart. Now, reinforced slope zonation to decide the spacing and the number of the reinforcement. So, you can provide the spacing in zone, let us say V, 2V, 3V, 4V, 5V, 6V. So, what will be the depth from the crest to the bottom of the zone? Let us say Q, then it will be Q by 2, that means 0.5 Q, Q by 3, 0.33 Q, Q by 4, 0.25 Q, Q by 5, 0.20 Q, and Q by 6, 0.17 Q. Then what will be the thickness of the zone? That means it will be the 0.5 Q, and then this will be 0.17 Q, that is 0.50 minus 0.33 Q, 0.17 Q. Similarly, 0.33 minus 2.5 Q is give 0.08 Q, 0.25 Q divided minus 0.20 Q, which will give 0.05 Q, 0.20 Q minus 0.17 Q will give 0.03 Q, and this is 0.17 Q. This is the thickness of zone. Now, how many number of the reinforcement? So, number of the reinforcements will be 0.50 Q by V, 0.17 Q by 2V, 0.08 Q by 3V, 0.05 Q by 4V, 0.03 Q by 5V, and 0.17 Q by 6V. So, you have to choose the nearest integer of the number of layer and add the remaining thickness to the next zone and repeat until it reaches to the top of the slope. And finally, add the number of the layer in each zone to achieve the total number of the layer. It will be more clear when I will give one example. Now, step 8, total horizontal force P can be determined from the following equation, that is P is equal to half into K into gamma H square. what minimum number of the reinforcement required in is equal to P divided by safe design strength of reinforcement, that means T design. Step 9, check if the condition is satisfied. That is, number of minimum reinforcement obtained in step 8 should be less than number of the reinforcement obtained in step 7. Then if it is satisfied, then your design is okay. Now alternative design approach, step 1, design the tensile strength. So allowable tensile strength of the geotextile T allowable is equal to T ultimate by reduction factor. So T design will be T allowable by factor of safety Fs. Step 2, determine of spacing and the number of the reinforcement. So required spacing SB at the base of the slope, SB is equal to T design by K required into gamma into H. The spacing can be maintained for the entire height of the slope. So number of the layer required N is equal to H by SB. H is equal to height of the slope and SB is the spacing between the two reinforcement. So you can determine that number of layer of the reinforcement required. Step 3, determination of reinforcement length. So we require the reinforcement length. Determine the reinforcement length from the dual chart. Select the reinforcement length arrangement as follow. When LR by H overturning, due to overturning, it should be greater than LR by H direct sliding. Then choose the reinforcement of a constant length, that means LR by H is equal to LR by H overturning. But when the LR by H overturning is less than LR by H direct sliding, choose the reinforcement as A constant length, that means LR by H is equal to LR by H direct sliding, or B length varying uniformly from LR by H base is equal to LR by H direct sliding to LR by H crest is equal to LR by H overturning. So you can then, based on the LR by H value due to the direct sliding or LR by H value due to the overturning value, so you can determine what should be the length of the geogrid. You know, if it is a LR by H greater than LR by H direct sliding, then LR by H will be LR by H overall, and if it is not, then you can think about the constant length, or you can think that how the length varying can be done in this method. So this is one example, design and embankment slope considering the given data. So this is the embankment and this is the height of the embankment, this is the slope of the embankment, this is the length of the embankment, and these properties of the soil, pi angle of internal friction, gamma unit weight of embankment soil, and Ru is pore pressure ratio. So in this problem it is given the height of the embankment H is equal to 7 meter, angle of slope beta is 65 degree, unit weight of embankment soil gamma E is equal to 20 kilonewton per meter cube, angle of internal friction of the soil pi is 35 degree, and we are considering here pore pressure ratio, that is Ru is equal to 0, and factor of safety Fs is equal to 1.3, tensile strength of the geogrid T is 30 kilonewton per meter, and spacing between the two geogrid material is 0.20 meter, and reduction factor is equal to 1.367. So this is the example, and now we will adopt the dual chart. So this is the dual chart is given. So step 1, you have to determination of minimum required forces, that is K required. So, effective angle of internal friction pi dash we have to determine. So, pi dash is equal to tan inverse tan pi by factor of safety. That means tan inverse tan of 25 degree divided by factor of safety 1.3 depending upon the type of the material you are using. So, this will give you that pi dash value is equal to 20 degree. So, this is the design chart which for RU is equal to 0, that is pore water pressure is equal to 0, and this is the slope angle is here base beta, and this is the minimum required force K required. So, we have to calculate what will be the minimum required force K required from this dual design chart. Now, we know that beta is 65 degree and pi dash is 20 degree. So, we know beta here 65 degree and pi is dash is 20 degree. So, you move up, and when pi is equal to 20 degree, then you move horizontally, and which will give you the value of the minimum required force, that is K required. So, K required will be equal to 0.3. This is K required is equal to 0.3 for RU is equal to 0. So, we calculate what is K required from this chart. Next, step 2, determination of minimum required length of the geogrid LR, that is due to overall stability, that is LR by H overall stability criteria. So, this is the dual design chart in which you can calculate what will be the minimum required length for overall stability, that means LR by H overall, and this is the slope angle, and this is the LR by H overall, and this is the pi value. So, here beta is equal to 65 degree, and you move up, okay, this is pi is equal to 20 degree, and then you move horizontally, you can have LR by H OB ERL is 0.85. So, LR by H, that is minimum length you can calculate for overall stability is equal to 0.82. So, we calculate the LR by H for overall stability is 0.82 from this design chart when RU is equal to 0. Now, next we have to calculate what will be the direct sliding, that means LR by H direct sliding criteria. Again, from this design chart, this is for minimum required length for direct sliding, that means LR by HS, and this is the slope angle beta, and this is the pi value. So, you know the slope angle beta is 65 degree, you move up and check that what is pi dash is equal to 20 degree, then you move horizontal, and then you can calculate that what will be the LR by H, that for direct sliding, that means minimum required length for direct sliding. So, LR by H direct sliding you can have 0.90. So, we check that what will be the K required, we also check what will be the LR by H for overall stability, that is 0.82. We know also what is LR by H due to direct sliding, that is 0.90. Now, you check that whether LR by H, that direct sliding greater than LR by H overall stability or not. Here you can see that LR by H direct sliding is 0.90. So, this is greater than the LR by H overall stability. So, if it is so, you can say that LR by H is equal to 0.90. If it is greater than this, then you can adopt LR by H 0.90. So, therefore, LR will be equal to 0.90 into height of the slope is 7. So, this will give 6.3 meter. So, you know the length of the geogrid material is 6.3 meter. So, you can calculate this. Now, step 3, determination of shape design strength of geogrid, that is T design, will be equal to T ultimate divided by factor of safety into reduction factor, and T ultimate is given is 30 divided by factor of safety 1.3 into reduction factor is given 1.367. So, this will give the T design value 16.88 kilonewton per meter. Step 4, determination of spacing constant, that is Q. So, Q is equal to T design by K required into gamma into V. This I talk about that what is the spacing constant. So, what V, you can assume this minimum spacing is 0.20 and K required is 0.3 is constant. So, therefore, you can calculate what will be the Q, that means what will be the spacing constant. So, this Q will be equal to this T is 16.88, this is 16.88, this divided by what is K required? K required is 0.3, what is gamma? Gamma you know 20, and what is V? That minimum spacing we consider 0.20 meter, so 0.20 meter. So, this way you can calculate that Q or spacing constant is 14.07 meter. Now, step 5, determination of spacing and the number of the layer. So, division of the entire length of the embankment into zone. So, this is the spacing of geogrid in zone in meter. Let us say V spacing we have considered 0.20 or 2V will be the 0.40 meter, 3V will be the 0.6 meter and 4V is equal to 0.8 meter. And next, that what will be the depth from the crest to the bottom of the zone. So, this is spacing constant Q. So, Q will be equal to 14.07, which we have calculated. Q is equal to 14.07. So, Q is equal to 14.07. Next, Q by 2 will be half of this, that means 7.035. Again, Q by 3 will be 4.69 and Q by 4 will be 3.517. So, here you can see that division of the entire height of the embankment into zone. So, when a Q spacing constant here, the spacing is V. Next, this zone Q by 2 when spacing is 2V. When this is Q by 3, this spacing is 3V. When this is Q by, this is 4, your spacing is 4B. When Q by 5, this spacing is 5B. When Q by 6, this spacing is 6B. When Q by 7, spacing is 7B. So, this is the division of the entire height of the embankment into zone. Now, you see here that we have considered only up to 4B, only up to 4B here, because you see that our height of the embankment is 7 meter or height of the slope is 7 meter. So, that means this we can consider 7 minus 4.69 will give you that what will be the thickness of that zone, that means this will give 2.31 meter. Again 4.69 minus 3.517 will give 1.17, that means this is the thickness of that zone, that is in meter, and then remaining 3.517. So, now if you add this 2.31, 1.17 plus 3.517, which will give you the summation of the zone of the thickness 7 meter. So, you are having the 7 meter. So, that is say that slope, this is the height of the slope is 7 meter. So, you can see it satisfies the zone thickness is 7 meter. So that is why we are considering up to the 4 of B, because we are not going beyond that, because the height of the slope is only 7 meter. So if it is a more, then you can go ahead with the defined value. You can go ahead with the q by 5, q by 6, q by 7, etc. So now spacing and the number of the layer. Now spacing in the zone, that is meter, and this is the thickness of the zone meter. This is calculated number of geogrid, and this is number of layer n, and this is the remainder in meter. So in general, that at the base of the steep slope, you have to provide one layer of the geogrid. So this we can say that calculated number of geogrid 1, so we take one layer of the geogrid at the base or in between the foundation and the embankment. So you can provide one layer. Now base spacing zone base is 0.40, 0.6, 0.8. So you know here that spacing zone, because from here, so 0.40, 0.6 and 0.8. So that is why the spacing in zone meter 0.40, 0.6 and 0.8. And thickness of the zone, this is thickness of the zone 2.31, 1.17 and 3.517. So here thickness of the zone is 2.31, 1.17 and 3.517. So next you calculate the number of the geogrid. I say at the base you should provide 1. Now here the 2.31 by spacing of the zone 0.40 will give you 5.775. So you take the number of the layer 5. So remainder is 0.775 into spacing zone 0.4, this will be the 0.31. So this is the remainder in meter. Now next, spacing in zone 0.6, thickness of the zone 1.17. So calculated number of geogrid 1.17 plus the remainder, that is 0.31, divided by the spacing zone is 0.6. So it will give 2.47. So we are considering number of layer 2 and remainder is 0.47 into spacing in zone 0.6, this will give you 0.282. Now next, spacing of the zone 0.8, thickness of the zone 3.517. So 3.517 plus that remainder is 0.282 divided by this spacing zone 0.8 will give 4.75. So you take 4. So then remainder is 0.75 into 0.8 is equal to 0.6. So here you can see that what will be the number of the layer. So if you add 1 plus 5, 6 plus 2, 8 plus 4, 12. So total number of layer will be the 12. So you have to place the total number of the geogrid in this slope about 12 layer. So provided the zone thickness from the bottom, you can see that 0.4 into 5 plus 0.6 into 2 plus 0.8 into 4 plus remainder is 0.6. So that means this will give 2 meter, this will give 1.2 meter, this will give 3.2 meter and 0.6 meter. So this will be the 7 meter. So you can see that zone thickness from the bottom is about 7 meter and total number of the reinforcement layer provided is 12 meter. Now step 6, you have to check for the number of the layer. Total required cumulative tensile strength for safety P is equal to half required into gamma into H square. K value is known 0.30, which we have determined from the dual chart. H is 7 meter and gamma is 20 kilonewton per meter cube given. So, P will be equal to half 0.5 into K required is 0.30 into gamma 20 and H is 7 square. So, it will give P equal to 147 kilonewton per meter. Therefore, required minimum number of the layer will be equal to P divided by T design. So, what is P? We have calculated now 147 divided by T design we know 16.88. So, this will give 8.71, that number of the geogrid layer. So, 8.71 say this is 9 number. As per our design method what we have adopted, and it is coming 12. So, it is less than the 12. So, we require about 9, but we are providing the 12, then it is the safe. So, design is safe. So, this is the layout of the geogrid reinforced slope is given in this figure. So, this angle of the slope is 65 degree, you know, and height of the slope is 7 meter, and as I said, at the base you have to provide one layer of the geogrid material. Then we are giving 5 layer of geogrid, 5 layer 2 and 4 like this. So, we are giving 5 layer at a spacing of 0.4 meter, and then the here is 2 layer at a spacing of 0.6 meter, and then here 4 layer at a spacing of 0.8 meter, and then remaining you can provide with the 0.6 meter. And tensile strength of the geogrid we consider about 25 kilonewton per meter. So, you know what will be the tensile strength of the geogrid material, you know what will be the spacing at the different height of the reinforced soil slope. So, then you can design like this. Now, I will show you that software for steep soil slope. This is Kuchibhatala has developed this software, and here in this software it is very interesting. With the same software you can design the slope at any angle as you like it, and also you can design the mechanically stabilized reinforced soil slope. So, now let us say this is the embankment property, height of the embankment is 12, and angle of foot for the embankment is 60 degree, and surcharge load is 10 degree, reinforcement properties, and the creep limited long term strength is 16, and here we are providing that some partial factor of the safety. Now, this partial factor of safety is what is called F of D, F of E, and also F of M. Now, this partial factor of safety has been taken from the BS code specification, British Standard Code specification, where that F of D here, which is 1.1, this is partial factor for mechanical damage, and this is F of E is equal to 1, this is for the environmental damage, and this is F of M is equal to 1, this is the partial factor for the manufacturer or the data interpretation. So, these are the factors you have to take into consideration for the design, and also you have to check that what should be the creep limited long term state, and this is the limit equilibrium method has been adopted. And soil field property, let us say unit weight is the 19 kilonewton per meter cube, pore pressure RU is 0, you can also vary, and the design shear pi dash is 30 degree and strength value is equal to this 0, and here also the check that interaction between the soil and the reinforcement, that is due to the sliding and due to the pull out value. So, before you use this, we have to check that what should be the data we have to consider for this design of a 12 meter height of a magmin. So, you can use this 2 parts wave solution by the Jewell given by 1990. This is the steep reinforced slope design chart for RU is equal to 1, pore water pressure is equal to 1. Let us say that we are considering here a height of the wall 12 meter and beta is equal to 60 degree. If beta is equal to 60 degree, we first of all determine what will be the minimum required force, K required, and when pi value is equal to 30 degree. So, let us say pi value here equal to 30 degree, and for 60 if you go up and for pi 30D, and then you can calculate K required, and let us say this is K required value is 0.15. I am just noting here from this chart that what you obtain, that is what is K required, you obtain 0.15 from this chart. This is the minimum required force, this is the minimum required force or 0.15, and RU value I say it is equal to 0. Next, for minimum required length or overall stability, that means LR by H overall will determine from this chart. So, we know the slope angle, that is beta is equal to 60 degree, and you move up when pi value is equal to 30 degree, and then you can calculate this what should be the LR by H for overall stability. So, LR by H for overall stability will be about 0.46. So, from this chart we can calculate that LR by H, and this is due to the overall stability. So, this will be about 0.46. And next, that we have to calculate the minimum required length for direct sliding, LR by H direct, LR by H direct. So, we know that slope beta angle is equal to 60 degree, and that pi value is equal to the 30 degree. So, then you can move in the horizontally, then you can have LR by H direct sliding is about 0.48. So, this you can have LR by H for the direct sliding is equal to 0.48. So, we know all this data. Then we know all the data, then we will substitute this value here. Here you can see for the design chart RU and K value, as I said, this is K required 0.15. So, we substitute this value is, that is 0.1 and 5, and then LR by H overturning 0.46. So, this is 0.46, and then LR by H direct sliding 0.48. So, 0.4 and 8. So, you substitute this value. So, you can calculate, you can see, you can calculate. You will obtain the depth of the geogrid layer, that is depth of the layer. Here you can obtain it. This is the reinforcement length, you can have it, and you can have also the anchorage length here. So, you can calculate what will be the total length of the reinforcement. So this is the total length of the reinforcement. Now you can see the figure. You can see the figure here. This is total number of the layer is 27, and if the spacing is more, so you are providing the secondary uniaxial geogrid material. So you know that what is the length, and this red color which will give the embankment length. So for this reinforcement, where here is the PC is equal to the 16, that is the creep limit long term stability, and at FD 1 point I say that partial factor of mechanical damage, this is FE for environmental damage, and this is FM is the manufacturer and data exploration. So you can use this design chart. So you can also place at any height, you can make it at any height. You can see, you can make any height, you can see how it is changing, how the design chart is changing, how it is changing. So you can make it. Okay. You can also define the surcharge load, also due to the surcharge load, how it is the changing of the curve. So this is very useful, and you can use this kind of the software in your problem. Also that you can use the same for, you can change the angle, you can change this angle. For example, if you wanted to make a 90 degree, let us say you wanted to make 90 degree. So if it is a 90 degree, okay, then you also keeping all others same, you can change it, and then you can calculate it, you can have, and then you can show the figure. You can see this is 90 degree. So this is the number of the layer of the reinforcement, this is the embankment length, and total number of the reinforcement length about 31. So you can make use of this software for the mechanically stabilized reinforced soil wall, and as well as for any steep slope as you like it. Apart from that, you can also determine, apart from that, you can also change this reinforcement strength. Suppose this is 40 RE. So I am just putting some of the value here. Let us say 0.3 K value, L by H value, let us say 0.5, and L by H direct sliding, let us say 0.6. So you can calculate this, and you can show the figure for this 40 RE. You can also change this, the reinforcement property, suppose 80 RE, you can do the 80 RE, then you can calculate and you can see the property. So you can see that. Now for the seismic aspect also, it can be shown, seismic also you have to take into account. So now you can say that seismic stability also you can want to calculate. So you can give that some value of the basic horizontal seismic coefficient in that zone, whether it is zone 1, 2, 3, 4 as was classified by IS. So let us say that seismic zone factor is 0.3. So then you can directly calculate, you can see what is the seismic thrust, that is kilonewton per meter, what will be the horizontal inertia force 591.52, total dynamic force 649.73, and dynamic force act at a height of 7.2. So you can also use this and also determine what will be the other forces. Okay. So this way you can make use of this software, and this software is very easy to calculate for any angle of the slope. Even then, if it is a 90 degree, you can use also the seismic aspect, and it is very user friendly. So with this I finished my lecture today. Any question, let me hear from you. Thank you for listening.